guys don't know, we have a couple little things coming up, and starting next week, next Monday, we are going to be 4 days a week, which we are super excited about having most of everybody back in the room. I will admit that once we're getting back to 4 or 5 days a week, that we'll be able to start doing a little bit more activities, a little bit more learning in the classroom. Um, Kids that are virtual, still not a big deal. We'll still have class just like normal. You'll still be available to participate and do everything just like we normally do. Okay. So I'm really looking forward to that. Looking forward to somewhat getting back to normal. I think we all need that on there. So, all right. So today we on your weekly schedule. So again, if you check that out for today, you will see that we have. Just let me go ahead and pop it up here. So again, we got our check-in. Make sure you guys always do your check-in. It should only take you about 30 seconds anyway. Uh, we have some little note on the formation of, actually I should change that, not really formation of solar system anymore. It's actually the formation of early Earth. Let me double check that, make sure, yep, you're getting that one on there. Then we have an early Earth formation handout. So this handout here, go ahead and open it up and pop it up. These are going to be some guided notes on the early Earth formation. And again, we talked about some of this stuff already a little bit. Okay. But these are going to be the big ideas, the main ideas I want you to cover for today. And again, we are going to do this during the notes, and then you submit it, turn it in today. There really should be no late work. There really should be no falling behind, because this is literally what we're going to do for today. I am hoping that the notes do not take the entire class period. I'm hoping that you guys get to work together for a few minutes and kind of just talk to each other about what you got for your answers, and discuss, hey, what should we put down for this question, that question, etc. So again, that's my goal, is to hopefully give you guys about 5-10 minutes to kind of still work together and complete this handout by the end of the day, turn it in, get credit for it, and again, hopefully not falling behind already. So real quick, I'm going to go shut my classroom door, and then we'll get started with some stuff here. Yeah. Alrighty. So today, and if you look at the weekly schedule, you'll see that Wednesday we got a little activity game that we're going to play and work on together. We're going to do that on Wednesday. Friday, we're going to kind of wrap up a little bit about the rest of Earth, formation and stuff. So again, if you see Wednesday is going to kind of be the break, and then this slide down here, number 26, you're going to start Friday stuff. So we're going to try to get all this stuff 1 through 24 done today. Friday, a little activity, and then go from there. Okay. All right. So Earth's history. We're not going to get into super detail about all the little aspects of Earth's history, but we are going to cover the basics. And the standard that we're trying to hit and cover today is talking a little bit about natural resources and how humans are using those natural resources and why the resources are where they are today. And a lot of it has to do with Earth's history and what has gone on with Earth, how Earth was formed, and what gone on in the 4 billion years since then to allow humans to use those resources. Okay, and those are mostly the things that we're going to focus on today. So we're going to focus on early history. We're going to focus on how Earth got the materials, the oxygen, the carbon, the things that we use to live. And then we're also going to talk a lot about plate tectonics. And I know you guys probably know the basics of plate tectonics, but we're going to kind of get into nitty gritty a little bit more on that. and trying to really make sure we understand kind of what's happening and why it's happening. Okay. So our plan for the week, again, Monday, try to get through 1 through 24, Wednesday, little activity, and Friday, talk about Earth's atmosphere on Friday. So follow along with me as we kind of cover these notes here. I'm going to kind of keep my screen like this. Hopefully you guys can see it okay. Mainly just because I want to be able to see your screen as well at the same time as this on here. So just real quick, I'm not going to go over all of this, but I just want to kind of talk about some basic Earth facts that you might not be aware of. So Earth, as you guys know, the third planet from the sun. The distance from the sun is approximately 93 million miles. That was one of the Who Wants to Be a Millionaire? $1 million question, was the distance from the Earth from the sun, about 93 million miles. The orbital period for how long it takes to go around the sun is 365.25 days. So you know there is a decimal, there's a fraction there, and it's 0.25, which means that every 4 years we get an extra day. And you guys probably know that. That's called leap year. And that was last year. Last year was leap year. And so 3 years from now, and February 28th or 29th, whatever day that is, we'll have another leap year. Okay, so it is a fractional and number of days that it takes. So we do have to add a day every 4 years. Okay, so rotational period is almost 24 hours. It's not exact. And also, rotational period, it would not always 24 hours. The time that it takes to rotate around the sun changes, and it actually is getting longer and longer and longer as time goes on. But again, you're talking about a change over millions of years. Morning. How about change over millions of years, the day getting longer and longer? So for us humans, it's not really a major factor that we need to worry about. Okay. The other things that we want to kind of know about, like our current atmosphere today, about 77% nitrogen. So it is mostly nitrogen, which is an inert gas. It does not react with us as humans, so we do breathe in mostly nitrogen. But 21% oxygen today, and about 2% other gases. Things that separate Earth is that we have lots of different crustal rocks. We have a magnetic field. We have plate tectonics. We have a hydrosphere, which is a sphere where water is located. We also have a biosphere, where life is located. And water and life makes Earth unique, and that's part of the blue planet idea there, is that not all the other planets have a hydrosphere or a biosphere. So it is kind of interesting how unique Earth really is. So the very first thing we want to talk about is the age of Earth. So it's estimated that the age of Earth and rest of the solar system as well is about 4.55 billion years ago. And the way we know that is from lead isotopes. And we'll talk more about those in a couple of minutes on there. The oldest rocks that we find, that we observe, are about 3.8 to 3.9 billion years old. And again, you can literally find those rocks. Okay, go measure them. Okay. The oldest minerals that we find on Earth, which are also called zirconium, okay, are about 4.2 billion years old. Note that the minerals are older than rocks. The minerals are actually formed on the interior of Earth, and then they come out of Earth every now and then when you have volcanic eruption and things like that. And the oldest moon rocks are about 4.4 billion years old. Note that the moon rocks are older than Earth rocks, and that's going to make sense later on. And that's mainly because Earth rocks are being recycled, and they're changing. All the other planets, they do not have plate tectonics, and those rocks do not change over time. Okay. Earth early timeline. Again, we talked about how Earth was formed from a planetary nebula, from a Cleft star. Remember, or not a Cleft star, but a star that's supernova. Okay, and gravity brought all that stuff together about 5 to 6 billion years ago. Okay, about 4.6 billion years ago, the sun began fusion, so we had a protostar, and a proto-Earth was formed about the same time. We do have the Earth-Moon impact, and I think we're going to talk a little bit more about that again today, because that causes Earth to melt. And so Earth was solidifying, but then it collided, and that impact was really bad for Earth. Okay. And 4.2 billion years ago, Earth was completely differentiated. What we mean by that is that there were different layers of Earth. So it took, it took 400 million years for that to happen. About 4 billion years ago, early as ocean, water started to form, the atmosphere started to come be there, call it the hydrosphere. About 3.8 billion years ago, we start getting life. About 2 to 3 billion years ago, we start getting photosynthesis, which allows oxygen to start being in the ocean. About 2 billion years ago, oxygen hits the atmosphere. So oxygen is actually a relatively newer molecule. It wasn't really there when Earth formed. So oxygen is relatively young. So we're going to discuss more of these in depth this week and next week. But the main question we want to focus on today is how do scientists know these events? How do they know these years? Okay. How are they just making stuff up? Of course, the answer is no. They're not just making stuff up. Okay. So how do we know the age of rocks on Earth and when these events happen? What we're looking at there is actual data, and a lot of it has to do with fossil records. Okay, and when we're looking at the age of rocks and the age of fossils, we can start putting pieces together what happened when. Especially when we're talking about photosynthesis, life, animal, plant, those type of things. But you got to remember that not only plants and animals, they're not the only things that fossilize. A lot of things fossilize. You can even fossilize another rock inside a rock. So you can actually trap things with other material and kind of preserve that record. Okay, especially minerals and really unique types of metals and things like that. You can actually trap them inside rocks and then analyze them later. Okay. So what we're doing here is radioactive decay, radioactive dating. And we're actually going to play a game on Wednesday about this. So the process of unstable elements like uranium, they do decay to become more stable, like lead. You guys probably know lead if you've ever gone fishing or hunting. Lead is a really common metal that they use. It's a soft metal, but it's really stable. Okay. You want to be careful about putting lead in your mouth, especially if you're a fisherman. You probably know this. A lot of people like to bite down on the sinkers, bite down on the lead and on their fishing line. Really probably shouldn't be doing that because lead is so stable that it stays in your body forever. So every time you take a little bite of the lead sinkers, or you're touching lead ammunition with bullets essentially, every time you're touching those lead particles, they're getting on your hand, they're getting in your mouth, that kind of stuff, and the lead literally stays in your body forever. That's how stable it is. And then, of course, if you do that again and again and again and again and again and again, you can get a lead buildup in your body, especially as you get older, and that can cause issues. That can cause problems later. Okay? So lead is super stable. But scientists know that it takes a certain amount of time for unstable atoms to decay to stabilized atoms. So it takes a certain amount of time for uranium to decay and turn into lead. I can actually show you that, not with uranium, but I can show you that with unnatural atoms, and we can literally measure it becoming more stable. And if we know how long that takes, we can figure out how old the rocks are and the fossils are, or whatever it is that we're looking at. Okay? And that's how we get this idea of how old they are. So the half-life of uranium is about 4.5 billion years, and that is the time that it takes for half of uranium to decay into lead. Okay, so if I have a rock of uranium and it's mostly uranium, then that's a very young rock, a very young chunk of uranium. If I have a chunk of rock and it has some uranium but a lot of lead, that means it's a very old rock because it changed from uranium to lead on there. And atoms do that, and it's called radioactive decay or radioactive dating. So one of the cool events that we know in Earth's history is from radioactive dating is the giant impact formation of the Earth-Moon system. I'm gonna try to see if this video works. I haven't tried it yet today. You guys are my first class, so let's see if the video works. It looks like it. Yeah. All right. Of course.
That face that is usually covered by her phone has finally made an appearance.
So it's just a couple minutes. You guys see it? You guys probably can't hear it. It doesn't matter. There's no words. Again, no gravity. Gravity. Like rock and roll. That's really loud. uh, hopefully you guys saw that, but you guys have a link on there if you can't really see it. So, what's that? Yeah, it's a video. Yeah, no, it's a video. Yep. All right. It's like rock and roll music, but yeah. So how did Earth perform? So remember we talked last week about the giant impact of the Moon and Earth system. We talked about how the ratio of the size of the Moon compared to Earth is actually really large, and doesn't really make sense that the Moon would get trapped into our gravitational field, being as big as it is. And so scientists believe that, and based on data, based on rock formation, things like that, especially when we went to the moon, that there was an impact about 4.5 billion years ago between what was a protoplanet Earth and protoplanet something else, and they ended up hitting each other. And when they ended up hitting each other, though, it caused both objects, Earth and the moon, to melt. Okay, and that's important because they both also solidified and made rocks at the same time. So Earth rocks and the moon rocks are about the same age because they solidified at the same time. Now, Earth rock or the moon rocks are a little bit older than Earth, and that's because of recycling. And we'll talk a little bit more about that later. That does occur. Earth does recycle its kind of go in there. All right, so very, very early Earth. Basically, not only the moon but Earth both were basically nothing but magma. Very about 4 billion years ago. Okay, so they were basically liquid rocks, magma after that collision. Okay, and then from there, Earth will eventually start to cool down. Okay, and then go from there. So, Earth, early magma ocean, early Earth was incredibly hot, mainly due to the friction of accretion, all that gravity bringing that matter together, especially the bigger pieces of matter, and that creates a very high temperature planet. Okay, so early Earth and early Moon and early planets are basically constantly being bombarded by material because gravity is bringing all that stuff together. Okay? Now we're not bombarded by things as much because there's just not as much out there anymore. Gravity already brought it all together. Okay, there is still stuff out there, okay, and we're still keeping an eye on them. But early Earth was very, very hot, but it did eventually start to cool down. Okay, as the Earth began to cool down, okay, the heavy metals and the heavy dense objects, just like anything, if you have a soup at home or whatever, okay, things that are heavy are going to fall to the bottom, things that are light are going to float on top. Well, Earth is a molten liquid basically, and so things are going to separate. Okay, so in the center you got your heavy metals, especially iron. Now there's a question there. Okay, let's see if you guys know it in the chat box. So real quick in the chat box, why was iron very prevalent in early Earth's history? So think about that real quick. So try to put it in the chat box. Why was iron very prevalent in early Earth's history? If you need a little hint, Okay. I kind of know what you're talking about there, Ben. So if you had to follow along with the note, the answer is there down there at the bottom. Yeah, Logan found it. I think that's what Ben's trying to say too. Anybody else? Just three people paying attention. Do I need to do the extra credit thing again? All right. So iron is very prevalent because iron was the largest element that was made by that previous star that blew up. So if you remember the large star, the supernova, they make up to element iron. And then we know that that star ran out of energy. We know that star was done making element because it blew up. And so iron was one of the largest elements that that star made. So it made a lot of iron in that previous star. So everything in our solar system had a lot of iron in it, especially the rock planet, the first four rock planets that are in the asteroid. There's a lot of iron in those. Okay. And again, that's also one way that we can find asteroids. We can find those things laying on the ground using a metal detector looking for iron, and that's how people find meteorites and things like that. So the previous star made a bunch of iron, and Earth has a bunch of it. It's gravity brought it all together. And then iron is heavy, so as Matt and Ben said, the iron started to sink down to the bottom or to the center. Okay, it started to fall to the center, and then iron is basically at the core of Earth right now. The lighter stuff, like silicon, oxygen, those type of things, the lighter elements ended up floating on top. Okay, aluminum, those type of things. Okay, and then that is what turned into our land, is the lighter stuff. So the really, really dense stuff is in the center, and then it gets a little bit less dense, 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 and then eventually the least dense material is floating on top, just like a cup of water or a bowl of soup or whatever else. Okay, got your liquid in there, and the interior of Earth is a liquid formation, a liquid rock. At the bottom, your heavy vegetables and stuff like that sink to the bottom, and then your light veggies and stuff like that, float on top. It's the same type of idea here. So iron accumulated. You can see the little iron droplets here. They accumulated and they fell to the center of Earth, and basically became our core. We call that differentiated. So the inner core is solid. The rest of this is molten, okay? But the interior solid is as dense as can be. That's a solid, okay? The liquid is a little bit less solid, but notice that it is differentiated. It is in layers, okay? And so Earth's interior, we'll talk more about how we know this Friday, but Earth's interior is in layers and it's separated by density. Okay, and we have lots of different layers. You guys probably know the mantle right underneath the crust, but even the crust had different layers based on their density. And then obviously water is the least dense, and then air is even denser than water, so air is way out here, right? So it's all separated by density, Earth's interior. And yes, we can actually kind of know what's inside it. The other thing about Earth, and that's really good news for us, is that Earth also has a magnetic field because the iron is in the core. And iron produces magnetism. Okay, all magnets have iron in them unless they're other rare earth metals. Neodymium is a rare earth metal. But your regular normal magnets that stick on your refrigerator at home are made of iron. Okay? And that produces a magnetic field. And so luckily, Earth has a magnetic field, and that magnetic field is protecting Earth from solar energy, from radiation, and it deflects a lot of that material away from Earth so that the solar energy, solar radiation does not come into Earth and hurt us as humans. So us having an iron core in the center is excellent for Earth. Without that magnetic field, we would not have water, we would not have air, we would not have life, we would not have anything here on Earth. Scientists believe that Mars started the same way, that Mars used to have a magnetic field, and Mars used to have an atmosphere, Mars used to have water and all that good stuff, but Mars lost its magnetic field due to the differentiation of density. And then when it lost its magnetic field, that it lost its atmosphere, it lost its water, lost anything that might have been growing on it. So the magnetic field is probably the most important thing that we have to protect life on Earth. And so we're thankful that there is a lot of iron in that core to produce that. All right, we also have a lithosphere. And again, lithosphere is the lighter subject, it's the rock layer. Okay. And again, after that differentiation, the lighter stuff ended up floating on the liquid density, the higher dense stuff. You're talking about liquid rock. That's pretty dense. Okay, it's not water underneath there. It's rock. So the lighter rock started floating, and then started creating layers. And one of the layers that I created was the lithosphere, which is the rock layer. Okay, the crust, another word for it, is composed of lighter elements such as oxygen, silicon, aluminum, calcium. Those are all much lighter, much less dense objects. Okay, so this crust layer, called a lithosphere, is actually floating on the mantle, the liquid mantle below it, which has a high dense molten rock. So as it floats, just like an ice cube in water, just like an iceberg in the ocean, as it floats, the land, the rock, the iceberg, whatever, think about it, all that stuff can move. And that's really important for our lesson today, is that things move, and they're constantly moving, and they're still moving today. Okay, is that rock on top of the ocean, top of the mantle, is still moving today. It is also really important for a kid to realize that underneath the water, there's land. You'd be surprised at how often kids don't realize that there's land everywhere on Earth. It's weird because most of Earth is water, but there's land underneath the water. Okay, so if I took away all the water, this is what Earth would look like, with no water on it. Now, let me ask you this question. This is not what early Earth would look like. Why not? So real quick in your answer box, why is this not what early Earth would look like? Early Earth did not have water. So it looked kind of like this, but it would not look exactly like this picture. Why not? Well, that is true too, man. There wouldn't be any snow because snow is the water. Yeah. All right. So if you could tell, and most of you guys are getting this idea here. If you could tell, like, that's United States, that's South America, that's Africa, that's Asia and Europe and Australia. Early Earth did not have the continent that we have today. You guys probably already know Pangea. You probably heard of Pangea when they all came together as supercontinent. That happened multiple times. Pangea is the most recent one with the dinosaurs. But these land masses, they move and shift like crazy. And we're actually going to watch a video next week on the history. It's about 12 minutes long, though. All right, so on Earth, we do have a lot of water, obviously. But I like this map here. This map shows you the height. And so we got mountain ranges over here. Some of the tallest places in the world are in the Andes Mountains here in South America. And then obviously in the Himalayan mountain where Mount Everest is located. So we have mountain ranges. And then of course we have really flat areas like top of Europe and Asia. Flat areas here in like Florida and stuff. When the ocean starts to rise, these flat areas are going to be the first one to go underwater. Okay, because they're really low to the ground, really low to the water. Okay, and so we have mountain ranges here, and as you notice where the mountain ranges are located, most of them are located on the edges of these continents. And there's a reason for that. There's things going on that's creating those mountains. Okay. We do have the Appalachian Mountains right there. They're not really that tall. They're really not. They're pretty small. They're actually getting smaller every year. So, the age of the oceanic crust, if you look here, the red lines are the youngest crust, the youngest rocks on Earth are the red lines. Okay? So the red line are the youngest rocks on Earth, and you know that most of them are in the ocean. All right? Pretty much all in the ocean. You got maybe a little bit close to the borders here of the United States being super young. But almost all the land that's the youngest stuff is in the middle of the ocean. And that is because the land is moving away from each other. And then when they move away from each other, the magma comes up and it hardens and it makes new land. And when they move away from each other, the land comes up, the magma comes up and it creates new land. When they move away from each other, magma comes up and it creates new land. Okay, so the new land is where the splitting is occurring. Okay, and it's just like a puzzle piece, and I know you guys have seen this before, but South America fits right there with Africa, right? You could just put those two pieces together, and we have proof of that based on the age of the rocks that are there, that indeed, the new land there, and if you rewind the clock of making new land, take it away and you get the old land, right? And they start coming back together. And so that's right, land can be older or younger, and that's the recycling that I was talking about earlier. So as the lithosphere moves, some of the rock can be pushed downwards. So you see this rock layer here. When they hit each other, sometimes they can go under, and this is called a subduction zone. And we'll talk more about that in a second. Okay. So they can actually go downward, and they will start to melt. Okay, when they start, so this older rock or whatever it is, doesn't really matter, but this rock will start to melt and it will become newer rock, especially when this type of stuff happens, when you have a volcano, you're basically making new land with volcano. Hawaii is getting bigger every second of every day because it's making new land with the volcanic activity. A lot of places are doing that, but especially Hawaii. Hawaii is getting bigger every day because it's making new land. Not that we can live on it, it's volcanic rock, but it is happening. Also, when they run into each other, sometimes they can go under. That's called subduction. And also, when they split away from each other, okay, you end up with a crack, or what we call or end up being a ridge eventually. The magma can come in and fill in that area and create new land. So as things move, old rocks get melted, new rock come in. We got this constantly cycling. And so the oldest rocks on Earth are about 3.8 million years. Okay. So on Earth, on North America anyways, note that we have different types of rocks here. These brown area here, the American Craton, okay, that is the oldest rocks in North America. Then the purple rocks, I guess, are a little bit younger. And then the green rocks are really young, and the blue rocks are a little bit younger as well. And so we do have different age rocks here in America. If you go to the Grand Canyon, you can actually see some of those layering in the Grand Canyon area. And then there is a question here about this edge right here. That is where the Appalachian Mountains are. And they are mountain because that's where the edge of the continental plate used to be, and it used to make a mountain. Well, now these rocks are all pretty old now, and so the Appalachian Mountains are actually getting a lot smaller today, mainly due to erosion from wind and water. Okay. So two land masses actually ended up hitting there and creating the Appalachian Mountain. Scientists think the Appalachian Mountain used to be the tallest in the world. All right, so this is a picture here. We're not going to do a whole lot on this, but note that the arrows show you the direction of the rifts, the direction that the plates are moving. Note that America is moving away from Africa. And again, just like a little puzzle piece, this part of America can fit on that part of Africa millions and millions and millions of years ago. This part of South America fits on that part of Africa millions and millions and millions of years ago. Okay. Right now, and I would have to move this a little bit, but it doesn't really show you this right now. But right now, the Iranian plate and Eurasian plate, they are hitting each other and they're making the Himalaya mountains right now. Okay, you see this Indian plate moving upward? It is hitting the Eurasian plate, and it's the Himalaya mountains are getting bigger and bigger and bigger and bigger every day, every year. So we have trenches over here. Marianas Trench is where we have two plates that are meeting as well. So the plates are constantly moving away from each other. And then, of course, because all these are moving away, the magma is coming up and making new land. Okay, magma is coming up, making new land. Magma is coming up, making new land. All right, we got just a couple quick more slides here. The land masses are still moving today. Again, earthquake epicenters. Note where all the earthquakes are located. They're located where the land is moving. Okay, they're not located on the interior of the continent very often. They're located on the edges where the plates are running into each other, where the plates are running into the ocean and things like that. The Pacific Ocean is getting smaller every day. The Atlantic Ocean is getting bigger every day, getting wider. Okay. Eventually, North America will hit Asia. Again, you're talking millions of years. Eventually, South America probably going to hit Australia, but again, you're talking millions and millions of years from now. Okay, if not billion with a B. Recent volcanism, and again, volcanism is where two plates ran underneath each other. One started melting, and it creates a mountain range, but it also creates melting areas. Again, note that they're on the borders of the land running into the other continent, the other area. All right, this is the last slide. That took a little longer than I expected, but I apologize. I do want to try to get it finished, though. So where do land run into each other differently? The three basic ways they can run into each other. They can either move away from each other, and that's called a divergent boundary. Okay, so when they move away, that is going to create a trench or a ridge where the new magma rises and fills in the space. Okay, so a divergent boundary is going to have the youngest, some of the youngest land, youngest rocks on Earth. A convergent, when two run into each other, toward each other, okay, and one going to win and one going to lose. It's just the reality of it. You know, the denser one, the thicker one, the bigger one is going to win. The other one's going to slide under. So you have two plates that hit. You know, they're going to, one's going to go over, one's going to go under, when they run into each other. That is going to create mountain ranges. They're going to buckle together, okay? And that's going to create mountain ranges when they do that. And that can also create volcanoes. If one goes under and starts to melt, and you have a mountain, that can come up through the top as a volcano. And then the last one is the transform. That is where they're rubbing against each other, but they're not going towards each other. They're rubbing against each other, going in opposite directions. Okay? And that will create a fault line. This is very, very common for earthquakes when they're rubbing against each other. Okay? Sometimes they'll get stuck, then they'll snap and they'll rebound, and that creates an earthquake. Okay, so we have a couple different boundary types there. All right, I do apologize. That took a little bit longer than I thought. I was hoping to give you 5-10 minutes to wrap that up, work together. Hopefully you took notes together or while we were doing this. Hopefully you answered all those questions. Hopefully you can submit that assignment today, right now, and not have to worry about it. But again, this worksheet, the follow along notes are due on Friday. So make sure you finish those up, learn the notes. This video will be posted as well if you want to rewatch the video and get some more information about that stuff. All right, I apologize. I did go a little longer than I thought. If you guys have any questions, always reach out, get a hold of me, okay? And then I will see you guys. I'll see you guys tomorrow. All right, have a great day.